Hello, in this problem we are given our alkene ring reacting with two chlorine atoms as well as water. And the first step we can predict to happen in this reaction mechanism is that the alkene pi electrons are going to attack one of the chlorine atoms. And this is due to the relatively weak bond between these two chlorine atoms. So the pi electrons from our alkene ring will come and attack one of the chlorine atoms as the bond between these two chlorine atoms breaks, and the lone pair of electrons will then go to this chlorine atom, giving rise to our chlorine anion as well as our carbocation intermediate. Now, one thing to keep in mind in deciding which one of the carbons will actually receive the chlorine, we're going to want to create the most stable carbocation intermediate, and this would result from placing the chlorine atom right over here, thus giving this carbon the positive formal charge, giving us a tertiary carbocation. Now, one thing to keep in mind when looking at this molecule is that whenever we have a lone pair of electrons on an atom adjacent to the carbocation, we're going to go ahead and with resonance to create an even more stable molecule, giving rise to our three-membered ring. And we can see this through resonance happen right over here as the electrons from the chlorine come and attack the electrophilic carbon, giving rise to our three-membered ring, which is also called a halonium, because our halogen in this case, which is chlorine, has a positive formal charge. Now, in order for this structure to be possible, both of the bonds to the chlorine have to be in the same face of the molecule, or in other words, both bonds must be cis to each other. And we can see this right over here as both bonds to this chlorine atom are oriented towards the backside of the molecule, and both of the bonds to this chlorine atom are oriented towards the front of the molecule, and this will obviously alter the methyl group that is hanging right over here there as well. So these two molecules the chlorine atoms are cis to each other. Now what this is going to do is create some stereochemistry constraints on where the water molecule is able to attack in the next step of the reaction mechanism. So in the next step of the reaction mechanism, our water acts as a nucleophile attacking the electrophilic carbon. Now, deciding which carbon is electrophilic, if we go back one step, we can see that it is this carbon right here with the positive formal charge. Now, since this chlorine atom is oriented towards the backside of the molecule, the water is actually going to have to attack from the front, which will make the bond between the chlorine atom break, and the lone pair will actually go back to the chlorine. And vice versa for the other molecule, since the chlorine atom is oriented towards the front of the molecule, the water molecule is going to have to attack from the back of the molecule. And the same thing happens. The bond between this chlorine breaks, and the lone pair of electrons goes back to the chlorine. So this bond here towards the chlorine will stay the same. What's going to change is the bond between this carbon and the water. And we can see that right over here as we get rise to our two secondary intermediates, where in this scenario we can see that the water molecule attacked from the front side of the molecule, and the water over here attacked from the back of the molecule. Okay, and now we can see that the oxygen in both molecules has a positive formal charge. Now the last step, which will give rise to our final product here, will be deprotonation. So in the last step, we can see that our water acted as a nucleophile. In this step, our water molecule is actually going to act as a base, removing one proton from the hydrogen, removing one proton from here, and the bond right over here is going to go back to the oxygen, so we can have a net formal charge of 0. Now I drew it for both molecules. We can see here how the water molecule attacks the hydrogen, just removing one proton, giving rise to our final products. And we can confirm that these are our final products because they are vicinal halohydrins, which is basically saying that the two adjacent carbons, one has a halogen and one has a hydroxy group. which we can see here. And this is actually called a anti-addition because the halogen and the hydroxy are trans to each other, as we can see here. And I hope this makes sense. Thank you.